Welcome back to Behind the Fluids. In this video, we are going to delve a bit deeper into three fundamental concepts that are essential for understanding the behavior of fluids: gradient, divergence, and curl. These mathematical tools provide us with a powerful way to describe how fluid properties change and how the fluid itself moves. Let's explore each one in more detail. First, we have a gradient. As this visual suggests, the gradient is all about identifying the direction of the most significant change in the quantity. Consider temperature, as shown in the heat map. The gradient at any point will point directly towards the area where the temperature is increasing most rapidly. The length of this gradient vector also tells us the rate of that increase. Mathematically, for a scalar quantity like pressure P, the gradient, denoted by gradient of P equals nabla of P, equals to vector with components the partial derivative of P with respect to x, the partial derivative of P with respect to y, and the partial derivative of P with respect to z. The triangle symbol is often referred to as the nabla operator, and in the concise Einstein summation notation, the gradient is written as the partial derivative of P with respect to x, subscript y, where the index y acts as a placeholder for each of the spatial dimensions, implying a vector result. Next, we examine divergence. As these illustrations show, divergence helps us understand the behavior of a vector field, specifically whether there are sources from which the fluid is emanating or sinks towards which the fluid is flowing. For a vector quantity phi, such as the velocity field of a fluid, the divergence, written as divergence of phi vector, equals nabla.phi vector, is a scalar quantity. It's calculated as the partial derivative of phi subscript x with respect to x, plus the partial derivative of phi subscript y with respect to y, plus the partial derivative of phi subscript z with respect to z. The dot between nabla and phi vector signifies the dot product. In Einstein summation notation, this becomes the partial derivative of phi subscript y with respect to x subscript y, where the repeated index y signifies summation over the spatial dimensions, resulting in a single scalar value indicating the local source or sink strength. And finally, we arrive at curl. As these visuals demonstrate, the curl of a vector field allows us to identify and quantify the local rotation within the fluid. It tells us about the tendency of the fluid to spin around a particular point. The curl of a vector field phi vector, denoted by rotation of phi vector equals nabla cross phi vector, is itself a vector. Its components describe the rotation of the field around each of the spatial axes. The mathematical expression in a vector form involves the determinant of a matrix with the unit vectors ijk in the first row, the partial derivatives with respect to x, y, and z in the second row, and the components of phi vector phi subscript x, phi subscript y, and phi subscript z in the third row. The cross between nabla and phi vector signifies the cross product. In Einstein summation notation, the curl of the velocity vector v is expressed using the Levi-Civita symbol epsilon subscript ijk multiplied by the partial derivative of v subscript k with respect to x subscript j. The Levi-Civita symbol helps to select the appropriate components to represent the rotation in each direction, resulting in a vector. So, to summarize, we've explored the gradient, which points in the direction of the steepest change, divergence, which tells us about the sources and sinks in the flow, and curl, which describes the rotation within a fluid. These are the fundamental tools for understanding the complex behavior of fluids. Thank you for joining me on Behind the Fluids. I hope this more detailed explanation with the equation spoken out has provided you with a deeper understanding of gradient, divergence, and curl. Stay tuned for future videos where we will apply these components to analyze real fluid flow phenomena. Don't forget to subscribe.